right, so we know that the area that we can use an integral to find the area underneath the curve. But one application we can use now is to use an integral to help us find the volume of a three-dimensional object. Whoa, okay. Basically, you're using the area, what you know about area, to as one of the dimensions in your volume equation, or as one of the inputs to your volume equation. Okay, so what we're going to do today is look at cross sections. What that means is that we're going to take a two-dimensional object and stack them next to each other. Okay, so we use the area between the two curves. So if I think about this as my first curve, the bottom curve is 0. So if I take the area between the two curves, see this section right here is going to become the base of um, the shape that you want to pop out in the three-dimensional area. So take a look at these examples here. We have one little base right here, and what is going to pop out is a semicircle. So we're going to stack a bunch of semicircles with radius that is determined by the distance between the two curves. So if the distance between the two curves is greater, then the semicircle, of course, is going to be greater. Okay, these pictures are going to draw these like actual physical things are a lot better than my drawings. I'm sorry. Okay. So another way, like we can pop out any shape that we want. So I think about like if you were to draw, if I were to draw this length right here and then punch boom, the drawing, it would outward pop whatever shape you want to come out, like a rectangle. Okay, so the base of the rectangle will be the distance between the two curves, but what I'm actually going to use is the area of the rectangle or the area of the shape to figure out the volume of the entire curve. Okay, so our bounds are going to be between the small one intersection to wherever it says to stop, okay? You're going to have an infinite number of shapes coming out from those bounds, and it'll always be the same shape, okay? So we call that a cross section. So here's what we do. Okay, so if the cross section is perpendicular to the x-axis, the volume is the bounds from A to B of the area of the shape, so whatever shape is coming out with respect to x. So if the cross section is perpendicular to the y-axis, so instead of going, this one's hard to see, but instead of if I were to cut the shape or get the base of the shape coming out going perpendicular to the y-axis, then we're going to take the area with respect to y. And we're going to do some examples here. So some common formulas that we use, you know, like a square is x squared. So we just use s squared as s is the base. You can use whatever we want. You can use b squared if you want. Okay. The area for rectangle is a times b, for example. They go on. Well, let's do some examples. All right. So the following, we're going to use the same region over and over and then just use different cross sections that are being popped out of that region. Okay. So it says for the find the volume of the triangular shaped solid whose base is the region bounded by the lines 1 minus x over 2. So that has a y-intercept of 1 and the slope of -1 over 2. Okay, so my region is there. And then the second line is -1, a slope of 1/2. And then the last boundary is x is equal to 0. So this is what the base of my shape is going, or what my curve is going to look like. Then what we want to do is make a square cross section that is perpendicular to the x-axis. So 90 degrees to the x-axis, I am going to use the area between the lengths between the two curves, okay, as the base of it says of a square. Okay, so what's going to come out is a square. So I'm going to make another one. What's coming out in three-dimensional space is a square. What I need to find is the area of this whole green three-dimensional object. It would be like, you know, the three-dimensional object, kind of like this. Actually, it would be kind of like this purple one right here. Okay, similar, but not the same because the base is different. We have a triangle instead of a square root. Okay, so what we're gonna do is, I know that I want to take the integral, so the volume, which I'm just going to call v in the future, is equal to the integral of a of x dx with my bounds a to b. Okay, so v is equal to, my bounds are from 0, x is equal to 0, to x is equal to 2. That's where I'm going to start making squares, and then I'm going to stop making squares. So I do have one square, like the giantest square is over here. Okay, and then my teeny tiny little square is going to be at the end at our last bound. Okay, so a of x is going to be the shape that's popping out of the it's the green shape here, which is a square. So in the way that I get so the area is equal of a square is equal to s squared, or the base squared. Okay, so how do I get the length of the base? The length of the base is dictated by the area between the two curves. So the area between the two curves would be, my base is the top curve minus the bottom curve. It's the top curve minus the bottom curve. I don't know which helps you see it better. Okay, so the top curve is 1 minus, so I'm just going to write that the base is equal to 1 minus x over 2, which is the top curve, minus the bottom curve, which is negative 1 plus x over 2. When I simplify that, I get 2 minus x. Yeah, 2 minus x. Okay, so that's the length. Every single length here is determined by the equation 2 minus x. All right, so what I'm going to substitute in is s squared dx, because that's the area of the shape coming out. The volume is equal to the integral from 0 to 2, which is basically like the length of how long I'm making rectangles. So if I have the base, the height, it would be like the depth of my object. Okay. The base is equal to 2 minus x. And then in order to get the area of a rectangle, or of a square, you square the base. So I gotta square the base, dx. All right, we're gonna use a calculator. So I am going to pull that up right now. Okay, just in case, I know we haven't done any trig, but I'm gonna make sure that my calculator is in radians. And then I'm going to use a calculator to do the integration. I'm going to press math, and I'm going to scroll down to 9, or I'm just going to press 9. And then I'm going to say from 0 to 2 of 2 minus x. I'm going to add a set of parentheses squared dx. Okay, I think it'll work. Here we go. Yeah. Okay, so I end up with 2.6 bar, or 8 over 3. So I'm going to write that the volume is equal to 2.6 bar, which is equal to 8 over 3. I know you can do this integration the long way, but it is also going to be vital for us to know how to use a calculator to do this. So make sure you practice, okay? All right. Let's do a few more, like a lot more, and then, yeah. So we're going to use the same bounds. Okay, but this time we're going to make square cross sections that are perpendicular to the y-axis. So that means that the cross sections or the base of the square is going to go horizontally like this, and it's going to pop out like that. Okay, so I can see that the base this time is going to be the right curve minus the left curve. And the right curve and the left curve change places. So they don't change places. It's just that we have 2 right curves and 2 left curves. No, we have 2 right curves. We have 1 left curve. So at the bottom of the triangular shape, when I draw my horizontal lines to make my squares, I can see that I have a different equation than in the first quadrant. So to get the base of the green, well, first off, actually, it's kind of a lot of work. Here we go. I get y is equal to 1 minus x over 2. And what I need to do is solve for x. So when I solve for x, I get y minus 1 times 2. So 2 times y minus 1, right? Other way. Let's just do this long way. Okay, so I'm going to do y minus 1 is equal to negative x over 2, multiply by negative 2 to give me x is equal to 2 minus 2y. So we have to write our top line in terms of y. And then our blue line, y is equal to negative 1 plus x over 2. We're going to do the same. So I get y plus 1 times 2 is equal to x. So x is equal to 2y plus 2. So this equation represents the blue line. Okay, so next up, we need to take the integral of s squared dy plus the integral of s squared dy for the bottom squares and then the top squares. So the blue line has a base of, let's write it up here. The blue line has a base of 2y plus 2. Okay, so the equation 2y plus 2 minus 0, since the base of the squares always stops at x is equal to 0. Okay, so the base would just be 2y plus 2. So I'm going to go ahead and substitute that in for s. So 2y plus 2 squared, because when you square the base, you get the area of a square, and then the integral adds up the areas of all the different squares together. So I'm going to start taking the integral from negative 1 to 0, and then I'm going to switch to the second curve. So the base of the green curve is going to be, I'm going to use my equation in terms of y. So 2 minus 2y minus 0 gives me 2 minus 2y, right? So I have 2 minus 2y squared, because when you square the base, you get the area of a square. And then we take the integral with respect to y. So how long are we taking the area of those rectangles or those squares from y is equal to 0 to y is equal to 1, from 0 to 1. And then I plug that into my calculator. Again, I know that you can do this by hand, but I am going to just plug this into my calculator. Okay, so I'm going to do math 9 from -1 to 0. And anytime I'm working in terms of y, I honestly just do this in terms of x, and you'll get the same answer. So 2x plus 2. Close my parentheses and square that value. Dx plus the integral from 0 to 1 of, I better move this over, 0 to 1 of 2 minus 2y, close my parentheses and square it, dy, or dx. I just write it in terms of x. It comes out to the same, I swear. Okay, so I'm going to go ahead and calculate that, and I get 2.6 bar. So the area between, or the volume, this is not area, sorry, this is the volume, is going to give me 2.6 bar, or 2.666, or if you want to round it instead of truncate, 2.67, or I would take 2.6 bar. Okay. All right, next up, that's all I'm going to do for the calculator. You guys can calculate those on your own from now on. And then, but if you have questions, let me know. Okay, so same bounds. So I'm going to be going between x is equal to 0 and then our two equations, or two linear equations. And then out from that linear equation, I want to make a rectangle with a height of 4. So I am going to just draw myself a little rectangle down here and be like, the height is 4. And then the base is always changing depending on the distance between the two curves. So the base is going to be taken perpendicular to the x-axis. So it goes vertically like this. So we're going to take the top curve minus the bottom for the base. Okay, so the base is equal to the top minus the bottom. So I know that is 1 minus x over 2 minus -1 plus x over 2, which above we calculated out to be 2 minus x. Okay, so the top curve minus the bottom curve is always 2 minus x. So out from there is going to be a rectangle with a height of 4. Okay, and then the base always changes. So what I'm going to end up doing is saying that the area is the base times the height, dx, and my bounds are going to be between 0 to 2. 0 to 2. So I'm making an infinite number of rectangles between 0 to 2 and adding them up, and that the integral is what adds up all those different rectangles together. So I end up with the volume from 0 to 2. The base is 2 minus x, and the height is 4 dx. Okay, so I like to simplify this. I'm going to get 8 minus 4x dx, and then I get the volume is equal to, and I plugged that into my calculator and got 8. Okay, so that's another one. Let's do another one. We're going to have a rectangle. This time the height is equal to 4 minus x, and then the base is going to be perpendicular to the x-axis. So same. Just this time we're going to have two equations. Okay, so perpendicular to the x-axis, out is going to come a rectangle. Oh, that's almost a rectangle. The height is equal to 4 minus x, and then the base is equal to the top minus the bottom curve. Okay, the integral adds up all the curves together. So I get the integral from 0 to 2, and then for a rectangle, it would be base times height. And because we're moving from left to right, we need to make sure we write our integral with respect to x, okay? So the base is equal to the top curve minus the bottom curve, which we know now simplifies to 2 minus x. And then the height this time, they gave us an equation, is always going to be calculated by the equation 4 minus x. So now I'm just going to plug this in. So from 0 to 2, so that's like the depth, remember? And then the area base times height is the area of the shape coming out of our graph here. So the base is 2 minus x times 4 minus x dx. And this time I did not simplify this when I plugged this into my calculator. I plugged it in just like this. And I got the volume is equal to 6.6 bar. All right, next, let's do a few more. A semicircle. Okay, so this time, same deal, same base shape of this triangle, and we're going to take semicircles that are perpendicular to the x-axis. So again, we are cutting our triangle vertically like this, and then so the distance between the top curve minus the bottom curve is the diameter of the semicircle. Out pops a semicircle. Okay, so right here, out pops a semicircle. Now imagine an infinite number of semicircles being added between the two curves. Okay, so what I know is that a semicircle, the area of a semicircle is equal to 1/2 pi r squared, because pi r squared, and then you're taking a half circle, so it's 1/2 of pi r squared, okay? And how we get the radius is the distance between, is basically this distance. So I am going to take the top curve minus the bottom curve. There's a lot of different ways you can do this, but the base is equal to the top curve minus the bottom. And then because that gives you the diameter, I'm going to divide it by 2 to give us the radius. Okay, so r is equal to 2 minus x, because we've done that before, divided by 2. So that would be 1 minus x over 2. Yeah. Okay. So now we're going to get the volume. The volume is equal to, and I'm going to take the integral. Okay, remember that gives me the depth. So what I need to multiply the depth by is the area of the semicircle. So we get pi r squared times 1/2 for the semicircle dx, and then we need to include our bounds from a to b. Okay, so I am going to pull out the 1/2 pi to the front. We are integrating from 0 to 2, so x equals 0 to x equals 2. The radius is equal to 1 minus x over 2, and then I need to square the radius, dx. Plug that into the calculator, and I get 1.047. Some more. Isosceles right triangle whose leg is bounded by the region and is perpendicular, and the cross section is perpendicular to the x-axis. That was a lot to take in, and I forgot my graph. Okay. Try and fix that for y'all. Okay, so I have my graph. Okay. And what I end up with is the leg. Oh, let's change that color. The leg of the triangle is going to be cut vertically because it's perpendicular to the x-axis, and it's a right isosceles triangle. So that means that the leg right here and the leg coming up have to be the same length, and then we end up with our hypotenuse like that. So it's an isosceles right triangle. That actually ended up a lot better than I thought it was going to be. So I'll just draw an extra little model here. Okay, I'm going to take that right triangle. This is the top curve minus the bottom curve. Okay, so how would I find the area of this triangle? Would be the base times the height, which are the same. So the base squared, since it's isosceles, base and base, times 1/2. Okay, so I'm going to say the volume is equal to 1/2 times the integral from 0 to 2. That's the depth. Times the base. Oops, and the top curve minus the bottom curve. So top curve is minus the bottom is equal to 2 minus x. So I end up with 2 minus x squared. It's isosceles, you multiply the two. Well, it's isosceles right triangle, so you multiply the two bases together. And we need to take the integral with respect to x. All right, so I used a calculator. I got 1/2. I took the integral and got 8/3. So this gives me a volume of 4/3. All right, last two. So next we're going to take the cross section is going to be an isosceles right triangle, but this time the hypotenuse is the bounded region, is defined by the bounded region. Okay. And the cross section is going to be cut perpendicular to the x-axis. So this time, this line that is the bounded region is actually the hypotenuse. And what's coming out is a right triangle. So it'll look like that. And it's an isosceles right triangle. So this arm and this arm are the same. So this arm and this arm. Okay, so the two legs sticking up, think about like a flag that's been folded and is laying down like vertically like that. I don't have a good flag like that. Okay, anyway, so the hypotenuse is defined by the top curve minus the bottom curve. Okay, so the hypotenuse. And so I need to figure out what the two legs are, because I know that in order to get the area of a triangle, you have to multiply the two. In an isosceles triangle, you have to multiply the base times the height. So here's what I know. This is a 45, 45, 90, right? Okay, so I'm going to go ahead and draw myself a new model. 45, 45, 90. I have my hypotenuse, my leg, and my leg. So, and this is equal to a ratio of 1, 1, and root 2. So I can set up a proportion. I know that if the leg is A, that should be A over 1 should equal to the hypotenuse over root 2. So I am going to solve for, I'm going to cross multiply and get A root 2 is equal to the hypotenuse. So the leg is equal to the hypotenuse over 2. Right? Right. Next up, we need to figure out what the base value is. So I know that the hypotenuse is equal to the top curve minus the bottom curve. So this should be equal to, let's just rewrite it. Is equal to 2 minus x over root 2. So we use like proportions to help us. All right, next up, we need to take the integral. So the volume is equal to the integral from 0 to 2, because our shapes are coming out of our base from 0 to 2, okay? And the area of this triangle would be 1/2 the bases squared, dx. So I end up with 1/2 times the integral of 0 to 2. The base is 2 minus x squared over root 2 squared. So I'll just put the square on the outside, dx. So the volume is equal to 1 over 2 times the integral from 0 to 2 of 2 minus x squared times 1 over 2 dx. So I get the volume is equal to 1/4 times the integral from 0 to 2 of 2 minus x squared dx. Again, I used my handy dandy calculator and I got 0.6 bar, which I know is equal to 2/3. All right, last one. I know this is long, sorry. So same bound for our base, okay? And this time we're going to make equilateral triangles that are cut perpendicular to the y-axis. So I'm going to go dy, I'm going to cut dy way, and I see that dy is tricky because there are two different right curves, okay? So again, this top curve is y is equal to 1 minus x over 2. And then when I change that to be written in terms of y, I get x is equal to 2 minus 2y. And then the bottom right curve is y is equal to negative 1 plus x over 2. And when I write that in terms of y, I get x is equal to 2y plus 2. Okay, so I know I'm going to have to use this right here in my integral. Now the area of an equilateral triangle is, I gave it to you earlier, is square root 3 over 4 times s squared, and s is the base. The base is dictated by the distance between the right curve to the left curve. So we're going to split this up. For the bottom curve, the base is equal to 2y plus 2 minus 0, right? So 2y plus 2. And for the top part, the base is equal to 2 minus 2y minus 0. All right, so we're going to have to make two integrals. The lowest part that I need to build a triangle out of is this when y is equal to -1. So my lower bound is -1. My upper bound for the bottom part is 0. And then I need to multiply, I need to take the integral of the area of the triangle. So I'm going to take root 3 over 4 times the integral from -1 to 0 of the red, which is 2y plus 2 squared, because it's s squared, dy. Plus square root 3 over 4 times the integral of 0 to 1, from 0 to 1, okay, of the base, which is 2 minus 2y squared dy. Again, I used a calculator, and I got 2 times the square root of 3 over 3, which is equal to 1.154 truncated, or 1.555. Oops, 1.155. Whoa, I know that was a lot. These are kind of difficult to picture, so always do your best to draw a picture, okay? Just do your best and let me know if you have any questions. Bye.